Can you guys see my screen? Can you give me a? Okay. So let us wait for 2 more minutes and then or 3 more minutes, then we can start. Okay, so let us start now. Okay. Yeah, the audio is okay, right? You guys can hear me. Okay. Fine. Okay, so we will go through our second class today. And in this class, what I will go through is bag of words representation. But before I go into the details of the topic today, some information about the course logistics. So the papers has been provided in the Moodle, and I have started the paper voting process. So you guys can now start ranking papers according to your preference and provide the ranks. So the last date for providing the rank is Sunday, 31st. So by then, please provide your ranks so that we can allocate the papers to you by, I think, the plan is by next Monday, I will complete the paper allocation process. This is the first part. And the second part is that I think some of you have not yet provided the information, have not yet filled the course survey. I'm not sure if all of you have filled it. So whoever have not filled it, I would request you to fill it because we will freeze the course survey by Friday this week, and only students who have filled the course survey will be allowed to like further participate in this course. So please fill it as soon as you can, so that I can be sure that who are participating in this course for sure, and based on that the allocation process and further filtering will be done. I hope that is clear. Any questions you can ask me now. Okay, so if there are no further questions, then we can start the class today. Yeah, so the topic of today that I will cover is bag of words representation approach. And yeah, I mean, this is a very initial or preliminary topic in NLP, and I'm sure some of you at least have gone through what bag of word representation mean. So can I see a show of hands? How many of you have heard of terms like TF-IDF, BM25, these kind of topics? Interesting. So yeah, so today we will also have a fun class quiz today. So I think anyone who has already been acquainted with the topics, they will find it quite easy and to solve the class topic. But anyone who is not yet acquainted with the topics, I would uh, request you to please pay attention to the ideas so that you can like answer the class quiz. And yeah, so with that, let's get started. Yeah, so we were talking the last class about document representation. So what is document representation? So it is basically quite simple. It is just a technique of representing documents and storing this representation in a particular form so that a machine can easily acquire or easily retrieve this representation, and then you can do various kinds of interesting human tasks like information retrieval, classification, similarity, prediction. These kinds of high level tasks you can do once you find a good way to represent the documents. And most of the time this representation is in the form of vectors. So I will give you a document, and once I give you that document, what you will do is that you will find a way to take that document and convert it into a vector. A vector can be like a d-dimensional vector, where d can be arbitrary large size. And once you form this vector out of the document, you need to store this vector so that what happens is that you can do some mathematical operations using this vector to solve these various tasks like information retrieval, classification, similarity, prediction. So that is like the basic pipeline of why we want to represent documents. So fundamentally, what is a document? It is nothing but a collection of words, right? So it is just a collection of words or terms or tokens. I mean, various people call it in various ways. Words, terms, tokens. Like, so these things, these words, terms, tokens, these are like the smallest meaning-bearing units that kind of stand on their own. So given a document, it will have a lot of lines, lot of paragraphs, lot of sections, these kind of things. But at the end of the day, each of them can be broken into words, which are like the meaning bearing units, and they together they form sentences. Sentences together they form paragraphs, and so on. So this process of taking a document, taking a text of the document and converting them into tokens. This is called tokenization. This is actually the first step that any NLP pipeline or any NLP approach does. So the first step that any NLP approach does is tokenization, which is nothing but take a document, convert it into small individual meaning bearing units. So as an example, let's say this is a document which contains this sentence like, I did enact Julius Caesar, colon, I was killed, and so on. So this is just a dummy document you can think of. So once you give this document to the system will convert it into individual tokens like I did enact Julius Caesar, and so on. Right now, interesting thing that you can see is that the system also did something like remove the capitalization of J. This is the normalization part that the system does, and it also removes this spurious punctuation, right? So these are like some of the non-trivial tasks that the system does, like also in capital it removes this punctuation, right? So these are some of the things that the system is expected to do, which makes it quite a hard challenging task, because there can be errors and you need to remove those errors, right? The second hard task that comes with tokenization is separation of the words into tokens, which is quite easy in case of languages like English, German, Hindi. So these are the languages that are already white space separated. So tokens are separated by white space. So you can add a rule like everything separated by white space is a token. So that is like one rule that you can use to find the tokens. But if these are not this kind of languages, there are other languages like Chinese, Sanskrit, where these words are not separated by tokens. So you will have a sequence of characters continuously, and that will be the entire text. So how will you know where a word begins and another word starts? So where are the individual components of this entire series of sequence of characters? So it's quite hard to do. And there are approaches for doing it, of course, but this is quite a challenging process, especially in this kind of languages where there are no clear word boundaries like Chinese, Sanskrit, this kind of words, this kind of languages. And the second challenge comes in case of social media text. So social media text, if you are in Twitter or in other social media platforms, you will see that often what happens is that someone says something in English and then switches it to something else. So they write the text half in English, the other half can be in German, can be in something else. So this process of switching between one language and another language, this phenomena is called code switching. So this is a phenomena that is quite common in social media data. You will find it quite common in Twitter and all these microblogging sites. You will find this. And another thing that you will find is that there is something called transliteration. So this is like so English is written in Latin script. I guess most of you know the English is written in Latin script. So there are other languages which are not written in Latin script, like Hindi is written in Devanagari script, which is a which has different set of characters. So each script has their own set of characters. English has its own set of characters. Hindi has its own set of characters, and these different characters form different scripts. So now what happens is that someone writes it in English and then switches to Hindi, but they write the Hindi in English, and this is called transliteration. So then it becomes even tougher, because now how do you find what are the individual units of the text that has just been written? So that makes tokenization quite a difficult, challenging process. And since this is the starting point of most NLP, or not most, all NLP approaches, so if you can build a good tokenizer, that can be of immense help. And in fact, you can become quite famous if you can write a very efficient tokenizer for languages that are not English, for very low resource languages, right? Which do not have a lot of text, a lot of like machine readable text out there. So if you can write a good tokenizer, that will make your work very famous. Yeah. So now first you take your document and form the tokens. So then what you do is that you represent your document and the tokens in the form of a matrix, and this matrix is called incidence matrix, document incidence matrix. So what does it look like? So you have your tokens or terms in the rows, right? And you have your documents in the columns, right? Now, let's say there is a term called Calpurnia. So this term, if it is not present in this document, Antony and Cleopatra, then this will be 0. This term is not present in this document. But if it's present in the document, then this is 1. So this is a binary representation, 1 or 0, but depending on whether the document is whether the term is present in the document or not. So as an example, Calpurnia occurs in Julius Caesar, so it is 1. Doesn't occur in Tempest, so it is 0. As simple as that. Now, what it means is that you can represent a document in the form of a binary vector, which means that if a term is present, it is 1. If a term is not present, it is 0. And this vector, what is the size of this vector? So what is the size of this vector? So this vector size is how many tokens that you choose. So if you have 1,000,000 tokens, then your document will be represented by 1,000,000 length vector. Each of units will be either 0 or 1. Okay. So if you have any questions, you can just raise your hand and ask me. So let's move on then. Right. Now, how do you use this matrix? I mean, you have your matrix, that's great, but how do you use it? So basically, let's say you want some information and you fire a query that which plays of Shakespeare contain the word Brutus and Caesar, but not the word Calpurnia. So this is a query that you want answers for. And how can you answer this question? So you can answer this question in the form of a Boolean query. So your Boolean query will have this expression that it should contain Brutus and Caesar, but not California. So this is like a Boolean query that Brutus and Caesar and not Calpurnia, right? So how do you represent this? So already you can see that Brutus, Caesar each have their respective vectors. Brutus has a vector represented by the row. Calpurnia has a vector represented by its row. So what you do, you take Brutus's vector, you take Caesar's vector, and you take the complement of Calpurnia's vector. So this is how it becomes, and then you just do the Boolean operation and if you do that, you will come up with what? You will come up with all the documents that your constraint satisfies, which is Antony and Cleopatra and Hamlet. So this process is called this process of retrieving documents using this incidence matrix is called Boolean retrieval. And you can understand this is quite simple. I mean, you can see that it is quite simple, but interestingly, this approach is used even now, especially in your email clients. So your email clients has this Boolean retrieval process, which is used to extract your past emails. So let's say you want all your emails that have this term. So this is how it is done even now, at least in most of the email clients. So now let's understand some of the problems with this approach. What are the hurdles of this particular approach? So think about that you have a corpus of 1,000,000 documents, which is quite small considering the internet. You have a corpus of 1,000,000 documents, which is very, very small. Now each document can have 1,000 tokens, which is also quite small. So now you have 10 to the power 9 tokens. Easy. Now let's say you have 6 bytes per token, which is also quite modest. So now for this unique number of tokens, for all these tokens, you need a space of around 6 GB, 6 into 10 to the power 9, which is still okay. Now let's say that you have 5 million distinct terms, right? So these are the number of terms that these documents have. But let's say you have 5 million distinct terms in your collection, right? So that means that your incidence matrix has around half a trillion entries. So your incidence matrix will have half a trillion entries, and you need six bytes for each entry. So you can understand what amount of space you will waste. And why you will waste space, because you can understand that of those half a trillion entries in the incidence matrix, only a billion of them are occupied, because each document can have 1,000 tokens only. So that means that your incidence matrix, the entire huge matrix, becomes extremely sparse. Lot of underutilization going on. So that means which makes it a problematic approach. The second thing that you can think of is that your approach of retrieving documents based on Boolean query, this does not have this concept of relevance score. What is a relevance score? So let's say today you fire a query in Google, right? You fire a query in Google today. What happens is that you will get all the websites in a ranked order. You will not get a set out of it. You will get a ranked list. Now, if you get a set, then it is your job to find among what documents in the set which is important, which is a very hard task, and it will waste a lot of your time. But if you get everything in the form of a ranked list, then you can assume that the first document in the ranked list is maybe most important. So that is the most relevant. Then the second one, little bit less relevant, and so on. So for a user, it makes more sense to get documents in the form of ranked list instead of getting it in the form of a set. So that is what this idea of score is important. So given a query document pair, you need a score that indicates how much this document is relevant for this particular query, right? And ideally, what you need to do is that once you have this scores for each document in your corpus, you can just return the top k, which is like top k in your rank. So that will make the users that will improve the usability of your system if you can do that. Now, how will you form this relevance score? So we will cover that now. So some of the properties that this score must have. So one of the properties is that if like none of the query terms belongs to your document. So let's say you have a document, and in that document none of your query terms exist. So the score for that pair is 0. That document should not be retrieved because there is no overlap. Now, if some of your terms in your query is highly relevant, is recurring in the document many times, that is frequent. So some query term, let's say monetary, that query term is occurring many times in the document. So that means that document could be important, right? That is the second part. The third part is that let's say there are many terms in your query that is present in the document. That makes it quite more important, right? So these are some of the intuitions you need to keep in mind while you are forming this relevance score. And let's discuss a very prominent approach, which is the TF-IDF approach. So TF-IDF approach, it consists of like there are two parts in TF-IDF. The first is the TF or term frequency. The second is IDF or inverse document frequency. So TF-IDF consists of term frequency and inverse document frequency. So first we will go through term frequency. So term frequency or TF-TD, this means the TF of the term T in the document D. So TF-TD is like TF for the term T for the document D, right? So this can be easily thought of as, I mean, someone can postulate that we will use the count of the token in the document as the TF. So someone can say that if this term, let's say money, occurs in this document 50 times, then TF for this term for this document is 50, right? That is the raw term frequency, right? Now, what can be the problem of using a raw term frequency? So basically, if a term occurs in a document 10 times and another term occurs in a document, let's say once, so this term occurs in some document 10 times and some document once. So that doesn't mean that the document where it occurs 10 times, it is 10 times more relevant. So the importance does not increase linearly. So if it occurs 10 times, then it is 10 times more relevant document. That is not the case, right? So that comes to our mind that we need to do some form of a down weighting. So since the importance does not increase linearly, we need to add some form of a down weighting to it. So how do we do that? So since it doesn't increase proportionally, we need to reduce the importance. So we do it using this log function. So the log function, you can understand it's kind of a non-linear function. So basically what you will do is that, let's say you want to compute the TF for the term T, then what you will do is that you will make it 1 plus log of the raw frequency of the term. So what it means is that if your document occurs 0 times, if your term in the document occurs 0 times, then it will fall in the second condition. So this is 0. If it occurs once, then you have 1 plus log 10 of 1, which is 0. That means it is 1. If it occurs twice, then you have 1 plus log 10 2, which is 1.3. If it is 10 times, then there is 1 plus log 10 10, which is 1 plus 1 2, and so on. So basically what you are doing is that if it occurs many times, like 1000, then you are down weighting it to 4. So that is like the kind of approach you are doing here. So you are down weighting things by using the logarithm of the raw count. So if you can have a score if you can compute a score for all the terms in your document, all the TFs for the terms in the document, if you can do it, then the score can be like the summation of let's say you have a query and you have a document, then you have some terms that occur in both the query and the document. So you can take the summation of those common terms and take the sum of their TF values. And that can be a score. That can be a possible way to find this relevance score. So what I mean is that, let's say you have a query Q and a document D, right? You compute all the terms that are common in the query and the document, right? All the terms that are common, and then take the summation of the TF values of those terms, right? So that can be one possible relevance coding that you can think of, right? Now, what could be a problem of this approach? So the problem of this approach is the issue of frequency. So you are actually ignoring the frequency of the term in the entire collection, that is your corpus. So TF actually doesn't take into account all the documents that you have in your corpus. It only takes into account that individual document where you're computing the TF value of. So it is like a single document metric, but you need to take into account all the documents that you have in your corpus. Why? Because let's say that you have some term which is rare, that is, let's say some term like monetary, which is quite rare in as a token. So in that case, what will happen is that particular word, all the documents that have that particular word, if your query has the term monetary, then all documents that have the term monetary should be given higher importance compared to let's say some document that doesn't have the word monetary but have, let's say, some other terms that are of like high frequency, right? So as an example, let's say that your query has the term monetary and money, right? Your query may have the term monetary and money. Now, money is a word that is used in various contexts, right? So in that case, if you fire your query using TF, then probably you will get various kinds of documents. But since your query has money and monetary, so that means probably you are looking at economics based documents. So you are maybe not looking at other kinds of documents. So in that case, you need to downscale a word, downscale documents that has the word money, so that you can only extract those documents which has this rare word which you are interested in. So that is like the approach that TF kind of doesn't uses, and we will try to solve it by adding another component to this calculation. So as an example, let's say that your document has various kinds of words. Let's say your query and document both have various kinds of words like good, increase, money. These are like very frequent words. These you can understand that these are common nouns. These kind of words are quite frequent: good, increase, money. So now what you want is that if these words are used, then what will happen is that all documents will have higher weights for this, and as a result you will extract a lot of irrelevant documents. So you need to downgrade the importance for these words so that you can give higher importance to those rare words. So that is the thing that IDF kinds of solves. So what it does is that it gives high weights to rare words like monetary, and it gives low weights to frequent recurring high frequency words like good, increase, money, these kind of things. So that is done by using the document frequency. So document frequency means how many times this word monetary or this word good, increase, money occurs in all the documents that is present in your corpus. So it counts how many times this word occurs in different documents in your corpus. Right. So what is the formulation like? So the formulation is quite interesting. So what it does is takes the inverse measure of the informativeness of your word, which means that let's say you have a corpus size of n, where n can be 1,000,000 documents, and let's say that your term occurs 10 times, right? So that means it is quite a rare word, right? So then what you will do is that 1,000,000 by 10, right? And that gives this value high, that gives this value a higher importance weight. But if you have a very frequent word, let's say the word good, which may occur 10,000 times, then this will be 1,000,000 by 10,000, which means that this value will be low, right? So that is like the idea here. So basically a word that is quite frequent, downweight that word, while a word that is rare, upweight it. And you also apply the log function to dampen it further. So that is like the approach that IDF uses. So up to here, if you have any questions, you can fire away. If not, then we will move forward. So let's say that you have a large corpus of around 1,000,000 documents, right? Let's say you have a text corpus of 1,000,000 documents. So now what you want to do is that you want to compute the IDF for the terms, right? You have terms like California, which is occurring, which have a document frequency of 1, which means that it is present in one document. animal, which is present in 100 document, and so on. So how do you compute the IDF? The IDF is just log 1 million by 1, right, which is 6. Then you have animal 1 million by 100, which is 4. So that is how this metric is used in this particular example. So now that you have an idea of what is term frequency and what is inverse document frequency, let's come to the final formulation of the score. So the final formulation of the score is the term frequency multiplied by the inverse document weight. So TF weight is multiplied with the IDF weight, and they together gives you the score of a particular word, that is a particular term T in a document D. So this is the weight that you are finally managed to compute. So remember, initially what you are doing is that if that token is present in the document, it was 1. If the token is not present in the document, it was 0, right? So it was a binary value of 0 and 1. Now you have a real value. So it is obviously more than 0. So it's a real value that now represents the importance of that word T in the document D. And this is a quite popular weighting scheme in information retrieval, and various softwares use this. And there is an even more used variant of this called BM25, which is actually most commercial softwares use BM25, which is actually based on TF-IDF. And this is also called TF.IDF or TF into IDF. So these are the various nomenclatures that are used to express this. So to recap, initially in the case of incidence matrix, what you had is document, token present 1, token not present 0. Now what you have is document and token, they have a score associated with it. If the token is not present, then it is 0. Otherwise, you have a real value. That is you have a importance value of that token in the document. Now, which means what? Which basically means that initially your document is represented by a binary vector. Now your document is represented by a real vector. That is how the difference comes here. So the representation changes when you use TF-IDF. So think of your documents now in the form of a vector. So your document now is so your space is what? Your space is basically formed of tokens. So as an example, if these are your tokens, then your space is represented by these units. So you can think of Antony as a direction, Brutus as another direction in the space, Caesar as another direction, and your document Antony and Cleopatra, it falls in some point in that space. So this is a multi-dimensional space. So if you can think of it as a two-dimensional space, then there is an X and there is an Y, which in this particular case is Antony and Brutus, and your document falls somewhere in that space as a dot. So your document falls in somewhere in that space, a two-dimensional space, as a dot. And if it's a multi-dimensional space, then it will fall in that cube or hypercube, somewhere within that hypercube, a point in that hypercube. So that is how your document will look like when you visualize it, visualize this space. So as an example, so mostly what will happen is that even in this particular in this multidimensional space, there will be lot of sparsity. That means that lot of entries will be 0. So mostly your words, your documents will lie close in some subspace. So if you have like a 3-dimensional space, then and one of the dimension, you will have that most documents have 0 in that for that space. So for that particular token, most documents do not have any entry, so it is 0. So your documents ideally lie in a 2D space, but since some document at least a few of the documents have that particular token, then you will have some documents lie in that particular one of on in that direction. So mostly it will be clustered in a 2D space while being in a 3D space. So that is like that is what becomes out of this process. That is what results out of this process of representing documents. So now let's say that you want to retrieve documents once you have represented the documents in this space. So now what you need to do is that you have represented documents in this multidimensional space, and you have a query, and what you want to do is that you want to retrieve documents that that are relevant to that query, right? So one approach for this is represent your query as a vector. So you can represent your same query also as a high dimensional vector, right? And then match the vector for your query and each of the vectors for your documents, and calculate the similarity, the match similarity, or the similarity of those two vectors. So here similarity means that how close these two vectors are. So if two vectors are in the same direction, so if you have a three-dimensional space and two vectors are in the same direction in the space, then their similarity is very high. Since these two vectors are in the same direction, they have high similarity. That means their angle between them is 0 because they are in the same direction. Now, if two vectors are in perpendicular direction, that means that the angle between them is 90 degree. What means is that they have a lot of dissimilarity or very less similarity for these two documents. So this is an approach to calculate similarity between vectors. So to calculate similarity between vectors, what you do is that you calculate the cosine of the angle between them in space. So you first represent them in space, and then to compute the similarity, you just compute the cosine of the angle between them, between these vectors in this space. So if these two vectors are in the same direction, that means that the angle is 0, cos 0, 1, that means high similarity. If they are in the perpendicular to each other, that means that they have a lot of dissimilarity, that is very less similarity. That means that cos 90 is equal to 0, that means they are very less similar. So that is how you can find the similarity of your query and the document. Yeah, and we will explain it further. So you take your document, represent a document in vector form, right? And then you already have your you take your query and you represent it in vector form, sorry, and you already have your documents in this same vector form. You compute the similarity between the query and the document using cosine similarity, and use this cosine similarity value to rank the documents. So once you have all the cosine similarity values, you can just rank them and take, let's say, the top k, where k may be 10. So top 10 documents that are most relevant to your query. So that is like one of the popular approaches that a lot of people do. Now to do that, you also need to understand, now to compute cosine similarity, you also need to understand the idea of norm, or most importantly, L2 norm. So how many of you guys are familiar with L2 norm? Can you give me a show of hands? Interesting. So, can some of you tell me what L2 norm is? Like, let's say, Nikolai.
Yeah, hello.
Yeah.
So I don't really know it at the moment, but I worked with it a lot. So it's just that we use a vector, normalize it, and try to see the length of the vector, and then work with this length. And yeah, based on how long it is, we can say it may be more useful than another.
I mean, you're in the correct direction, but to recap, I mean, to rephrase your memory. So basically, our L2 norm is the distance of the point from the origin, right? So think of it like when you think of that, all the points that I just talked about, they lie in a cube, they lie in a sphere. So you have a three-dimensional sphere, a 3D. You imagine a 3D axis where there is a unit sphere, that is a sphere with a radius of 1. So you have a sphere like that. Now, what you are using L2 norm, what you are calculating is the distance of a point in that sphere from the origin. So if a point is very close to the origin, then it will have a lower L2 norm, and if it is exactly at the end of the sphere, that is at the 1 point, then it will have a higher L2 norm. So that is what it gives you an idea of the value or the length of the vector. Once you normalize it, everything is between 0 and 1. So it gives you just an idea of the length of the vector. Okay. Now, what you do is that, how you use it is that, so you use it to compute the cosine similarity between two vectors. What you do? So cosine similarity can be written as the dot. So let's say you want to compute cosine similarity between Q and D. These are two vectors. You want to compute cosine similarity. So what it will comes up is that dot product between Q and D. Dot product is just element wise product. So let's say Q has two values, that is Q is a vector of length 2, then D will also be a vector of length 2. Then each of the individual points in this vector will be multiplied together. That is the first element of Q multiplied with the first element of Q, and the second element of Q, and again multiplied with the second element of the Q, and we will take a sum of that. So there should be a so this operation dot product can be written as summation of element wise multiplication. This is the numerator part, and in the denominator you are computing the norm of the individual vectors, the L2 norm. Norm can be of various types. You can have L1 norm, L2 norm, L3 norm, so on. So L1 norm is just this summation without the square. So here you are computing the L2 norm. So you are squaring the individual units and taking the sum and then rooting it up. So that is how you are computing the cosine similarity. You are just computing the element wise dot product, and then you are normalizing them by the norm of the vectors. So that is how cosine similarity is calculated. And what is the intuition of this cosine similarity? So the intuition is that if two vectors, let's say Q and D2, if these two vectors are they are closer in space, that means the angle between them is small, which means that they will have higher similarity. And if two vectors, let's say D1 and D3, they are farther in space, which means the angle is larger, which means the similarity is smaller. So that is how cosine similarity is calculated. And yeah, so what you do is that you compute the vectors of this individual query and the document, and then you compute the cosine similarity to know that how relevant your query is with respect to the document. And this vectors are nothing but TF-IDF values. So that is how you do. So to reiterate, you have Q1, which is the TF-IDF weight of the terms in this query. Then you have the document DI, which is again the TF-IDF weight of the terms inside the document. You compute the norms of that, and then you compute the cosine similarity, so that you can understand how relevant this query is with respect to this document. Right. So now comes the quiz part. So I will request you to go into this particular website and then use this pin. Is this website working? I hope it is working, right? Can you give me a show of hands? Okay, some of you have written in the message it's working. Okay, great. So this is just a small test for you guys, just to know that whether you can understand, whether you have understood it properly. So let's say that you have a document 1 which says that Tim likes playing chess. You have document 2, we play chess. Document 3, Tim plays like Sarah. And you have a corpus size of 1,000,000 documents, right? And you have the document frequency terms given also. And you have the TF-IDF weights also given. TF-IDF calculations, the equations also given. Can you compute the similarity between D1 and D2? Can you compute the similarity between D1 and D3? So I will give you like 5 minutes. So you can just compute it and then give me a, if you have done it, you can just raise your hand so that I know. So I will show the link once more if you guys, some of you have not yet joined it. I see 24 people have joined.
Can you show the numbers again? Because it's impossible to calculate without
Sure,
seeing them.
So I will give you 5 more minutes. So once you have done, you can give me a show of hands. So have you guys filled your answer? So I hope most of you guys have filled your answer by now. So let me just end the survey and see. Okay, so we have various kinds of answers, I guess. So let me just show you how to do it. So yeah, so first the document frequency part. So this is already given in this particular table, right? So what you just need to do is that question. Oh, okay. So actually I have ended the survey. So then now you cannot submit the answer. You can answer it in the chat if you have calculated it. Okay. So if you guys have calculated it and right now the service is closed, so you can just answer it in the chat. Right. So yeah, the document frequency, you just need to take the log of 1 million by 10, because that's how the formula is defined. So to do that, 10 by 1 million, which is 5. And if you do individually, you will come at these numbers. So these are the IDF values obtained by applying this function over this document frequencies, with this value being fixed. So this is the N. Now coming the term frequencies. So the term frequencies for this particular term, team, like, play, chess, and Sara, these are the different terms. So term frequency for document D1 for team is 1, like is 1, play is 1, chess is 1. So here you can assume that playing has been normalized to play, because tokenization will do that. Tokenization as well as lemmatization will convert this playing into the term play, and similarly plays will also be converted to play. So these are the kind of terms that will come up once you apply the pre-processing steps. So now these are your terms: the team, like, play, chess, and Sara. And here you have 3 documents, D1, D2, and D3, right? So now what you need to do is that you just need to compute the similarity between D1 and D3, right? You just compute the similarity between D1 and D3. And after normalization, that will come up to 5.96. So I see that there is one correct answer. So who is this person? I'm not able to see it from the from the service. So if can you raise your hand if you or message me in the chat if you put the correct answer 0.596. Seems like the person who gave the right answer is a little bit shy to come up. Okay. So yeah, so that's how this particular similarity value is computed. So this is like a real world example for you guys to like have an idea how it is done. So just to take just the takeaway from this particular representation, so you can understand that this is quite simple and it can be easily scaled to very large documents. So there are right now techniques like parallel processing and distributed computing, techniques like MapReduce. These are the kind of techniques that can be used to compute these scores for a document repository of billion documents quite fast. So you can do it. So this kind of techniques is scalable. It can be done quite easily. But there are a lot of problems also. So the first problem is that there is no idea of semantics. That is no idea of meaning. What does it mean? It means that Harry weds Sally is equivalent to Sally weds Harry. So so here luckily this term this phrase is equivalent. That is Harry weds Sally and Sally weds Harry is equivalent. So even if these two are represented same, it doesn't create a problem. But if you have sentences like this, that doctor console the patient and you have patient console the doctor, so these are like same tokens, but the meaning is completely different and can be used in very different contexts also, right? So the documents where you have doctor console the patient will be very different from the documents where you have patient console the doctor. So also things like synonyms. So there can be terms. If you do not consider the synonyms for the terms, then what will happen is that even if your query and your document have the same term, but the document can have synonyms and your query can have some terms. So let's say there is a term X in your query and your document has the term Y. When X and Y are same, but since they are synonyms, you will not able to find any match. So these are the kind of problems that TF-IDF has, which other approaches kind of solves to some extent. But still, I would say that this approach or variants of TF-IDF are used extensively in the industry, and various IR softwares like Elasticsearch, Solar, these kind of commercial softwares or these kind of free softwares that are out there, they extensively use this TF-IDF and this kind of index creation or this kind of indexing of documents. So this is why this is important to know. So yeah, today I think we will cover up to bag of word representation, and I will provide some materials for you to go through, because from next class onwards we will go through neural approaches, neural approaches that are based on neural networks and deep learning. So what I want you is that go through the lecture materials that I have provided in Moodle, so that you have a prior understanding of some of the approaches, so that you can understand more when I will talk about those topics. So go through them and we will cover them in the next class. So if you have any questions, you can ask me right now.
Yeah, I have one question about choosing the paper we need to present later in the semester.
Yes, go on.
The choice is between 40 papers, and
Yeah.
I have spent the last week reading 18 of them, and I just can't decide. I don't have enough time in the next 3 days to read 20 more papers.
No, you don't have to read the papers. You just read the abstracts and the titles.
Yeah, but the abstract is not really enough to give me an idea if this paper is going to go well with my interests. You know what I mean?
I understand, but the problem is that it is not expected for you to go through the papers completely and then decide, because it's kind of a challenge that if you like the abstract and maybe some initial part of the paper, then you can take it up and then move forward for next 3 months. So that is like the idea.
Okay, well, I can do that. Thank you.
Sure. So any further questions? Okay, so if there are none, so I reiterate, I've already provided the papers, and the ranking time is already on. So you can provide the rankings, and by next week the allocation will be done. And also go through the lecture materials, especially the mandatory ones, because they will help you understand some of the background on the topics that your papers will have. And if possible, also go through the non-compulsory material, because it will give you a wider grasp over the topic. Okay, guys. So thank you for attending this class, and we will see you next week.